Okay, good morning everyone. Let's go. Final projects, weekly reports, grappling with physics engines. How's everything going? Questions, comments, verbal abuse? Verbal abuse, go ahead.
What's the difference between evolutionary robotics and reinforced learning?
Great question. Okay, so last time when we were talking about Twitch Plays Robotics, I mentioned in passing reinforcement learning with human feedback. Lots of terms here. Let's start with the L. Learning implies modifications to synaptic weights. Usually it implies nothing else. Sometimes it's also meant to be modification of synaptic weights and learning rules in synapses. Sometimes it's learning synaptic weights and the activation functions in neurons. Sometimes it's used to mean optimization or change to cognitive architecture, but usually that's it. That's the boundary of where learning ends. So learning compared to evolution, what's the main difference, at least from our perspective? Changing the body as well. So lectures 2 through 26 inclusive, we're going to finally get to what makes evolutionary robotics particularly distinctive or unique compared to most other approaches to robotics, where the physical structure of the autonomous machine is fixed, and we are learning something about its control policy, or all of machine learning and AI, which tends to focus on learning, changes to synaptic weights. The underlying implicit philosophy, which I'm trying to make explicit for you all in this course, is the assumption that if we want to create autonomous and safe machines here in the real world, we need to think carefully or automatically design both body and brain together, which again is sort of the underlying idea of the much older concept of embodied cognition. That's the difference. So the reinforcement in reinforcement learning, for those that know reinforcement learning, what does the reinforcement part mean of reinforcement learning?
Reward and punishment.
Reward and punishment, which is usually a single number, which is, again, not unlike a lot of what we've seen in all of the evolutionary robotics experiments we've talked about in this course. We're often boiling down the quality of the behavior of the robot to a single number, how far it moves to the right, how well it shakes a block up and down, you name it. That's not always true. When we talked about the transferability project, which I apologize we weren't here in person for, but in the transferability project, we saw multi-objective optimization, in which the objective function, which is measuring the quality of the robot and its behavior, there were actually multiple numbers that we were trying to optimize simultaneously. Often in reinforcement learning, there's a single number, which is how good or how poorly the robot or the AI model is doing at whatever we want it to do. That's not always the case. Does that answer your question? Okay. All right. Any other questions about the final project? Things that you're struggling with? I have reviewed all of those of you that are taking the course for graduate credit. I reviewed all your final projects and given you back feedback. Everything looks good. One thing that I saw mentioned in many of the projects was wanting to do collision detection between multiple robots, or the differentiable robot trying to manipulate an object. In the differentiable assignments, obviously you were writing your own physics engine from scratch, and we have a minimal collision detection and resolution algorithm. For the undergrads, just to give them an update on what's going on there, in the differentiable assignments, you're making a mass spring robot, meaning the robot is made up of a whole bunch of point masses that are placed at particular points in space. And then we're connecting neighboring masses together with springs and adding motors to make the springs increase and decrease in length. Collision detection at the moment is just whether or not the center of any of the masses passes below the ground plane. This would not be a collision. This would be a collision. When this occurs, you're applying a force to push the object back up or ignore or canceling out any more pushing into the ground. It's about as simple a collision detection and resolution algorithm as we can imagine. If you, I think one or a few of you proposed trying to do a swarm in the differentiable simulator, which is perfectly fine. How do you detect collisions between this robot and resolve those collisions? Any ideas? If you can cast your mind back to lecture 6 or 7 where we talked about physics engines. Ideas?
The naive thing would just be to pairwise compare all of the pieces, and if they're circles, you can just see if the distance is less than the sum of the radii.
Okay, we could look to see whether these two objects have collided, and if the distance between any pairs are less than 2r, the radii of these circles, then you've got a collision, which is pretty good. But what happens if you get to this situation? Looks like a collision to me, but it is not detected by your collision detection algorithm. Other ideas?
You could, to make it also like simple, you could just have like, just call like just define like the center of that triangle and then make a circle around it, and if those, this kind of like make them all like a circle each.
Okay, this is a good idea. Perhaps this is based on the idea of collision boxes, which we actually saw when we talked about physics engines. A great idea. Also, a little bit problematic. There are edge cases in which it's not going to capture certain things, but a good start. Okay, the point I wanted to make is this is not trivial. There is a whole literature in computer graphics and physics engines research about exactly this. How do you detect and resolve collisions? You don't have a lot of time left in the semester, so allow me to make a suggestion, which is modify the radii of the point sources to be just large enough that they're always touching their neighbors. That's not always going to be true because the length of these springs is sometimes changing, but you can easily set the radii so most of the time these objects are in collision with one another, which makes collisions with other robots relatively easy. Going back to what Nate mentioned, you can just look to see whether any pair of objects, one from one robot and one from the other, have a distance of less than 2r. Then you can count that as a collision and apply a resolution, which is to push them apart. You can either add those forces to the objects, to the points themselves, or you can add those forces to the spring. You can assume there's a force that's pushing the springs apart. It doesn't really matter. Just some suggestions for those that are wrestling with collision detection and resolution in the differentiable simulators. Okay. Any other tips and tricks I can offer? Anything else that's problematic at the moment? Going once, going twice. Okay. All right. So back to lecture. We are trying to finish up our long section here on open challenges in the field, and I was walking you through the Twitch Plays Robotics project last time, which is an attempt to try and scale up robotics and scaling it up by involving more and more humans in using human feedback to direct how robots evolve. I realized that there was actually a video example of Twitch embedded in the schedule. So just to refresh your memory of how this works, here's an example of Twitch Plays Robotics running. We exposed the crowd to the worm and the quadruped. We invited the crowd in the upper right panel to propose things that they thought they could teach the robots. And you just saw one chatter vote for crawl forward, which seems promising. And down here, if I speed this up a little bit, you can see that their vote to teach the robot to walk forward has now been sent to the robot. And the violet robot, we are trying to determine whether it is walking forward. And we will see in a moment that a couple people voted for no, the violet robot is not walking forward. Okay, you can go and watch this video snippet. It's embedded in the schedule. So just as a reminder for how the Twitch Plays Robotics project works, this is what the crowd saw. And as a reminder of the data set, we've got these two robots, R sub 0, the worm, R sub 1, the quadruped. The crowd is posing a whole bunch of commands, plain English, to the robots. For each one of those commands that was sent to the robot, some of these commands on the robot. We were running that robot with a whole bunch of random controllers. So the ends are random sets of random synaptic weights that were sent to the robot while the robot was quote unquote hearing a particular set of commands. And for some of these random controllers that were running on a robot under a given command, the crowd provided a bunch of reinforcement, either yes or no. We tallied up all the yes votes and stored that as an integer in S sub 1, and we tallied up all the no votes and stored that in S sub 0. That's the data set. Okay, just to remind you for where we were, we reviewed some of the statistics about what we got back. The most common command issued by the crowd was jump. So in the results we're going to see now, you're going to see how and whether the robot managed to ground the symbols JUMP in its own sensor motor experience. Okay, I ended last time by mentioning this filtering step down here. Among all the 56,000 controllers, random controllers we ran on the robot, we took out the subset of random controllers that ran on the robot when the crowd was issuing the command jump to the robot. And then we further chose from there the subset of controllers that were issued on the robot when it heard JUMP, and there was at least one vote. The sum of the no votes and the yes votes was greater than 0. At least one yes vote and at least one no vote. So far, so good? Okay, so now we have in hand a bunch of controllers. We went back and ran all of those random controllers on the robot, and this was offline. The users were not, the crowd was not seeing this. We collected all of the sensor data that was generated by those random controllers, and we took just touch sensor information and stored it in a binary matrix. So you can see here for the worm is made up of 1, 2, 3 links. In the binary matrix, we have 1, 2, 3 columns. Each row corresponds to one time step in the simulation, and we just recorded whether or not that touch sensor was firing. Here it was zeros and ones. In your code base, I think it's -1 and +1. Doesn't really matter. So now, for every random controller that was executed during jump, for which we have some feedback from the humans, we also have this felt experience. This is what the robot felt when the crowd was saying, yes, you're JUMPing, or no, you're not JUMPing. So far, so good? Okay. Okay, sorry, just to orient you, we're on stage 3 of this 4-stage project. In stage 3 here, we're going to try and get the robot to learn a relationship between what it felt, the command, and how the crowd reacted. Okay. Okay, sorry. Having problems navigating this morning. Okay. We'll get there. Okay. All right. For the worm, there were a total of 1,038 random controllers during jump that received at least one piece of sensor reinforcement feedback. So for each one of we have 1,038 of these binary matrices. The worm robot had 1,038 unique experiences. And for each of those experiences, we take all the positive and negative reinforcement and we collapse this down to a single value, which ranges between -1 and +1. An O of -1 is uniform negative reinforcement. 0 yes votes, 3 no votes, or 0 yes votes, 17 no votes, unanimous negative reinforcement. An O of +1 is unanimous positive reinforcement. 0 no's, 14 yeses, 0 no's, 131 yeses. That's an O of +1. So an O of 0 is a neutral, right? Split votes. 4 yeses, 4 no's, 17 no's, 17 yeses. So we have 1,038 O values that correspond to each of the 1,038 binary matrices. So far, so good? Okay. So let's have a look at the moment. Let's have a look at the relationship between each O and its corresponding T. Okay. On the vertical axis here, you can see that the vertical axis ranges between -1 and +1. And on the vertical label here, it says normalized reinforcement signal. So this is O over here. You'll have to trust me, there are 1,038 green dots here. So each dot corresponds to the result of one random controller running on the worm robot. T is a matrix. So on the horizontal axis here, the grad student, Joey, who worked on this project, she took that touch sensor matrix and collapsed it down into a single number, which is the proportion of time that the robot spent on the ground. For those of you that are working on the Up, Up, and Away project, this should start to sound familiar. How do you think Joey collapsed this binary matrix down into a single number? Percentage of time spent on the ground. We've got 3 columns for each of the 3 body parts that make up the worm, and 1,000 rows that correspond to the 1,000 time steps in the simulation.
The number of times that all 3 are 1.
The number of time steps, the number of rows that are all zeros. Exactly, right? So the proportion of all 0 rows in that T matrix. That becomes a single floating point value between 0 and 1. And she plotted that on the horizontal axis here. Now, Joey, the grad student, has stepped in, and she's made an assumption about the robot's felt experience. She came up with this way of collapsing the binary matrix, so we're cheating a little bit. We want to keep humans out of the loop, but we wanted to see for ourselves first whether we could see any relationship between the behavior of the robot. So the further to the right the points are, the more time the robot spent on the ground, and the vertical axis, which is the way in which the humans provided feedback to that behavior. Is there a relationship? I see some of you sort of squinting and maybe nodding. What's going on here? Did the 434 people we got feedback from, were they just bots? Were they just typing things in at random?
And there's a correlation line drawn through here that seems to fit the data. I'm very confused by the sheer number of ones and negative ones.
Okay. There's lots to see here in this figure. So we plotted this trend line here. Although it's a little difficult to see, there is a negative correlation here. Generally speaking, the further to the right a point is, the further down that point tends to be. You can see there's kind of a cluster down here and another cluster up here. Not so many points up here and not so many points down here. A little bit of a negative correlation. Is this good news for us investigators or bad news? This is good because?
Because if it's jumping, they say jump. If it's not, if it's off the ground fully, then it is. Then people say, "Oh, it jumped." If it's not, it didn't.
They didn't. The more the robot jumped, the more of the proportion of the time it spent on the ground, the more negative feedback the crowd tended to give. The more often the crowd was saying, no, you're not jumping. So the fact that we could fit this line and it was a negative slope, that's what we were hoping for. It worked. Of course, it's not a perfect correlation. If it was it's not a perfect anti-correlation. If it was a perfect anti-correlation, what would you expect to see in this figure? It's not, so you don't see it. Perfect diagonal. You'd expect to see all the green lines along some diagonal with negative slope. That's definitely not what's going on. What a surprise. Humans tend not to always agree with one another. Nate mentioned he was confused a little bit about the fact that most of the O's, most of the summed reinforcement, was either a perfect one or a perfect -1. And there's also kind of a cluster here at 0. Why? Why not a more uniform spread along the vertical axis? Think about the humans that are involved in this.
Few votes.
Few votes. So for the vast majority of these a little over 1,000 controllers, there was usually only one piece of reinforcement. Either there was only one person on the stream at that time, or only one felt sufficiently emboldened to offer a yes or a no.
Could it also be like kind of groupthink? Because like, if I'm thinking like, it's kind of jumping, but everyone else is saying yes, so I'll just say yes because everyone else agrees with that.
Great observation. Anecdotally, we saw a lot of that. During times on the stream when there were quite a few people on it, we would see things like yes, 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 and then one person would say no, and the others would say, why did you say no? And the person would type in why they thought it was no, and then sometimes they would change their vote. You definitely saw chatter among the chatters, and sometimes they would change their vote, seemingly in response to peer pressure. Again, this is all anecdotal. Somewhere we have the raw transcript of every single chat and everything that everyone said, scrubbed of any personal details, all anonymized. If you're interested, shoot me an email and I should be able to dig it up. It's a wonderful document to read. Okay, so this was us sort of doing a sanity check. Again, baby steps like your final project, making sure that there might actually be a pattern here for the robot to learn. An ability to ground this symbol in its own felt experience and to ground it guided by human feedback. Okay. These were the 1,000 or so controllers under jump for the worm. We had about the same number of random controllers executed on the quadruped for the same set of symbols, JUMP. What's going on in the case of the quadruped? Different set of controllers, different body plan, same set of symbols. No idea whether this was the same set of humans or not. What's going on?
There's a lot more neutral ones.
A lot more neutral ones. I think you're right. Could be, or they might just be a little bit more spread out, possibly.
And the correlation seems to be very similar, but it also seems to like shift to the right a little bit.
Shifted to the right. So unfortunately, when we plotted the horizontal axis down here, the grad student did not keep the same horizontal range. This is a rookie mistake. When you plot everything, if you create multiple plots for us, please make sure to keep the horizontal and vertical axis ranges about the same for exactly this reason. Often we want to look whether a pattern stays the same or differs across multiple figures. A little hard to do here because of the shift in the range of values on the horizontal axis. So apologies, you're gonna have to do a little bit more cognitive work here this morning. So one non-difference, one thing that is the same, is there's a little bit of anti-correlation. Again, it's not very strong, but it's there. So that's good news. That means that for at least two different body plans, there seems to be a relationship between human feedback and the felt experience of the robot. other patterns you've noticed?
There's not really a clump in the top left.
There's not as much of a clump in the top left. Yeah. It's a little bit of a weaker anti-correlation.
The time grounded is generally higher than the previous robot.
Absolutely. So the points for the quadruped tend to be shifted a little bit further to the right. Why do you think that is?
It's harder for that morphology to jump.
Harder for this morphology to jump. Yep, exactly. Okay. Imagine that the robot had actually run some machine learning algorithm, not a machine learning algorithm, had run an algorithm that found this anti-correlation between its own experiences, between all the horizontal positions of these points, and the vertical positions of these points. Every time the robot hears JUMP and has this particular experience, the crowd says, actually, uniform negative, and over here and over here. So imagine the robot has now discovered this particular line. What does JUMP mean to the robot? Some of you may have been following the public discourse around whether ChatGPT understands language. Let's have the same discussion about our worm robot here. Does it understand what JUMP means? And if it does, what does JUMP mean to the robot?
It just like stay to the left. And in this case, it's a graph, so it wouldn't just say left, but like stay in that general range of like synapses and stuff.
Stay to the left of this graph, you mean, for the robot?
Yeah.
Okay, that's one idea.
Like spend as little time on the ground as possible, or like
Spend as little time on the ground as possible.
which means like
How does the robot know to do that?
make your touch sensors all negative.
Make your touch
as
sense. So
much as possible.
there's something about points being further to the left seems to correlate or have something to do with JUMP, but what exactly does it have to do with JUMP? What does JUMP mean to the robot? I tend to put scare quotes around all these things: understand, predict, mean. No scare quotes today. What does it really mean to the robot, literally?
Aren't these still random controllers?
These are still random controllers, absolutely. There's no evolution here. There's a little bit of learning. It's learned that there's a relationship between the horizontal position of each of these controllers and the vertical position of these controllers. It's not arbitrary.
But didn't you say at the beginning that learning is the changing of synaptic weights? Like that hasn't happened yet.
True, good point. Yes, sorry. This line, whatever we want to call it, it's found this relationship between the horizontal points and the vertical points. This is just linear regression. If you want to call that learning or not, we'll say the robot has run linear regression on this data to which it has access. Let's say the robot is still thinking about JUMP and it executes yet another random controller, and that controller causes it to spend 40% of the time on the ground. The robot just does something arbitrarily, and it's able to now place that point horizontally. It says, okay, that particular controller caused me to spend 40% of the time on the ground. No humans around. What is the robot thinking at this point? How does it estimate the vertical position of this point? Based on the line. So it has this line. The robot has discovered that there is an anti-correlation between the rightward position of the point and how far down it is. The robot spends 40% of the time and uses this line to try and reason about JUMP. The robot predicts that the point would lie here on the line. If you were able to ask the robot now, What would it tell you about this particular behavior it just performed?
Probably a jump.
It would say probably a jump, but we're not quite there yet, right? We're trying to stay grounded in the data. It's got JUMP. It spent 40% of the time on the ground.
I would just say it's like it did a good job at what it was supposed to do.
Getting closer. It did a good job. How does it know that it did a good job? 0.3. It says if there were people around, more often than not, they would do this. If the robot runs a random controller and it spends 100% of the time on the ground, what would the robot tell you about that controller relative to JUMP? If there were humans around, they'd give more than unanimous negative reinforcement, whatever that possibly means. Yeah? If you've ever spent any time around dogs, they'll do something and then they'll look at you. And you can sometimes see in their eyes, they know. They know how you feel about what they did. Yeah? So for this robot, trying to keep things literally and metaphorically grounded for a moment, if we want to try and talk about we want to talk about the relationship between JUMP, the literal felt experience of the robot, touch sensor data, JUMP and touch sensor data, and quantitative human feedback, the robot can determine that there is a relationship between these three things. And again, you can form your own opinions. My opinion is that that is what JUMP means to the robot. That is understanding JUMP. It's maybe not a profound understanding, but the robot can more or less tell you or try to show you it knows what JUMP means by doing a bunch of things and making predictions about human feedback or social repercussions of its actions. Everybody see that? You don't necessarily need to agree with me. We can all disagree about what it means to understand language. That's a different discussion. This is the one of the embodied approaches to trying to understand language or enable robots to understand language. Questions, comments, differing opinions?
I just wanted to ask, so like, are you trying to get the robot to do the same type of jump every time you ask it to jump, or just to jump? Because like, how I would think about it is the robot would get itself to like the highest jump number, and then be like, oh, jump, I'll just keep redoing that number. Even though like they're random robots, I get that, but like
Right.
eventually it would just be like, oh, that one was the best, I'll just keep using that.
It could absolutely, right? It could try and act on its knowledge. Here we're not trying to get the robot to jump. We're just trying to see whether the robot could discover or find a relationship between these three things: symbols, sensory information, social repercussions to its actions. Yeah? It's jump according to Joey, the grad student, right? Joey determined that jump means the proportion of time for which the robot spends on the ground. As we talked about last time in the Up Away project, there are other human definitions we could come up with jumping. And you can see from the actual vertical heights of these points, the humans here also don't agree about what counts as jumping and doesn't and isn't jumping.
Was the strategy here that instead of evolving one jump and having people say whether that one jump is a jump, it's like you're trying to recognize a bunch of different chairs, so you're trying to get the robot to be like, this is a chair, this is a chair, this is a chair, this is a chair, instead of evolve one chair?
Yeah. So it's a question about our goal. So our goal here was this.
Why do this instead of just have the people give feedback as lots of random robots are evolving synapses towards one jump?
Maybe we could have done that. We wanted to try and introduce as little bias as possible. The moment we make a fitness function for jumping and evolve robots for that jumping function, then it's the crowd deciding whether or not that's jumping, and they either agree with us, who wrote down the fitness function, or not. There's still bias here, again, because of Joey's decision about how to collapse this matrix. We're going to remove that last bit of bias, or at least the last bit we can see, in a moment. There's one more set of results I want to show you, but I just want to make sure we understand what our goal was here in this project. Symbols, sensation, social feedback. Yeah? Okay. So if you're willing to entertain the notion that this line, the fact that there is an anti-correlation between touch information and O, normalized human feedback, is it the same? Is the understanding of jump the same for the worm and the quadruped? Do both of these robots, I'll put the scare quotes back on, do both robots understand JUMP in the same way? Does it mean the same thing to these two robots, given the definition of understanding we just provided?
Slightly.
I see some of you doing the South Indian nod, right? Kind of yes, kind of no. Why kind of yes, kind of no? I also agree, kind of yes, kind of no.
It's seeing the same trend, but the data points are all different.
Absolutely. So again, if you were able to ask these robots, and you can't ask them, but if you were, they'd say, yeah, mostly we agree. It's an anti-correlation between the amount of time we spend on the ground and the number of no votes we get back. But we disagree on the y-axis intercept of these lines. If you look at, so this anti-correlation here intercepts a little bit above 0. This one intercepts a little bit higher. It's not much, but it's a difference. I found this interesting because it immediately means for these two robots, JUMP does not mean the same thing. Now that's either a quirk of the particular humans that reinforced this robot and the particular humans that reinforced this robot. Maybe it's an artifact of the fact that they were running slightly different controllers. Maybe it's an artifact of the fact that they have different bodies. Maybe it's a little bit of all of the above. We don't know. We haven't done that study yet. For me, the more interesting outcome would be because of their bodies. In retrospect, maybe that's not so surprising. If you have a different body plan, jumping is going to mean different things to different people or different things. Yeah? So far, so good? Any questions about this particular set of results? Okay, last bit, and then we'll move on to collective intelligence. As I mentioned, Joey has introduced her bias here by her definition of what jumping is. The number of rows in the binary matrix that are all zeros. Let's try and remove Joey's bias. The next thing we're going to do here is we're going to actually do some learning. So back to Cam's comment here. We created a very simple neural network. This is not a neural network that's controlling the robot. That part's already done. We've got the 1,000 neural controllers for the worm, about another 1,000 random neural controllers for the quadruped. We're going to create a little neural network here that has 3 input neurons and 1 output neuron with 1 recurrent connection. So we've got a total of 4 synapses, which means we need 4 weights, W for synaptic weights. We're going to take each of the 1,000 binary touch sensor matrices, which remember have 3 columns corresponding to the 3 touch sensors in the robot, and 1,000 rows corresponding to what values those touch sensors had at each of the 1,000 time steps in the simulation when the robot was running that controller. We're going to take each of those 3 by 1,000 matrices and push them through one of these random neural networks. We've got a lot of random neural networks on the go now. We've got the 1,000 random controllers for the worm, 1,000 random controllers for the quadruped, 1 random neural network that's going to digest each of the 1,000 binary matrices from the worm, row by row. We take the first row of the first binary matrix, plug it in, propagate down to the output neuron, where we're going to get some value between -1 and +1. We used the 10H activation function, which is going to make sure that this value, when we read it out, is between -1 and +1. So far, so good. We take the second row in the first random controller, plug that into the input layer, push it through this neural network, and because of the recurrent connection, it updates the output value of this neural network. Take the third row, push it through, fourth, fifth, sixth, seventh, 1000th row, push it through this neural network, and when we're done pushing all the 1,000 rows of one random neural controller through this network, we read out this value, and I'm sorry it's hard to see here. We're going to interpret this value as O prime. What do you think O prime means? This is kind of shorthand from machine learning. What do you think O prime means? The predicted crowd response, exactly. So in my little cartoon example here, let's assume for that random neural controller, the crowd gave back an actual O of minus 0.8, whatever that is. 7 no votes and 1 yes vote. Mostly folks believed that for that particular controller, the robot was not jumping. The prediction of this neural network, which is the robot's neural network, this is the social part of its brain, if you like. It's trying to learn how to predict how the crowd's going to respond to what it did. In this particular random neural network, it makes a prediction of 0.25, pretty far from minus 0.8. Remember, all these O's and O primes range between -1 and +1. This random neural network has low social intelligence. It has not predicted the crowd very well. So far, so good? Okay, we are not changing these 4 synaptic weights. We're leaving them as they are. We're going to take the second binary matrix for the worm, reset the output neuron, refresh everything, push it through again, get a second O prime, push the third binary matrix through, get a third O prime, push all 1028 random controllers, or all 1028 sensations through this neural network, and we have 1038 O primes, and we have 1038 O's. What do you think we do next? Not quite. Close.
Calculate the mean squared error.
Calculate the mean squared error. Calculate the error, or the difference between each O prime and O, which gives us back 1038 errors. And then, as Nate mentioned, we're going to take the mean of all of those errors. On average, how well or how poorly did this part of the robot's brain, its social intelligence, do at predicting how the crowd would respond to all 1038 things that the robot did. You can imagine that for 4 random synaptic weights, error is quite high. It doesn't do very well. So we could either use reinforcement learning or an evolutionary algorithm. Doesn't matter. In this experiment, I think Joey just used an evolutionary algorithm, like you're doing in your assignments. She evolved populations of length 4 vectors. She evolved populations of synaptic weights. She was evolving using a particular fitness function. What do you think that fitness function was? What do we want this neural network to do? Minimize error, right? So we're going to evolve a whole bunch of sets of synaptic weights, searching for a set of synaptic weights that minimizes mean squared error. That this neural network gets better and better at predicting social human feedback for more and more of those 1038 behaviors. Okay. Hopefully, most of you are wondering, how well did it do? How low could we get that error? What I just described is the training phase. We're training this part of the robot's brain to have high social intelligence, which is low mean squared error between the O primes and the O's. We get some mean squared error, 0.2, let's say. What does that mean? What does 0.2 mean? Is that good, bad? I have no idea. So like in most machine learning experiments, we're going to do one last experiment one last test called testing. We actually didn't train this network on all 1,038 binary matrices. We picked a random subset of them and set them aside, and only trained this network on the remaining binary matrices. And then after training, after we had tuned these 4 synaptic weights, we're going to take those held out or hidden sets of binary matrices, feed them through here, and get O primes. So we're going to take this trained part of the robot's brain, and we want to see how much social intelligence the robot actually has. The robot's going to play back some of the things that it did. It's going to feed into this trained network a bunch of these held out binary matrices. And how are we going to know? We're going to get something back here. How are we going to know whether this network was trained well or not? What would we expect to see?
Hopefully it predicts O correctly in the test.
It predicts O correctly, but correctly how?
Low error.
Low error compared to what? How low does it need to be able to say, yes, the robot has actually learned something about the relationship between what it did and how the crowd responded? Let me flip the question around for you. Let's imagine that training failed. These are just all synaptic weights. The robot didn't learn anything. It couldn't find any, this network could not find any relationship between all the T's and all the O's. If you then took this failed neural network, you don't know that it's failed, but you took it and feed it in new T's that it's never seen before, what would you expect to get out here? What would the O primes look like compared to the O's over here? What error would you expect to get during testing if nothing was learned during training? Similar or worse. Let's try and be quantitative here now. We want to be able to say with confidence, did this thing learn or not?
Errors would be higher than a random guess.
Errors would be higher than a random guess?
The errors of the random guess would be higher than that.
The errors of a random guess would be higher, right? So if this thing hasn't learned anything, you would expect that it's going to spit out O primes arbitrarily between -1 and +1. Comparing that to the O's, you would expect a difference of about 1. If you're making random guesses between a value of -1 and +1, and I'm picking a value between -1 and 1, you have no idea what value I've picked. We played this game over and over again. My O would differ from your O prime on average by a distance of about 1. Everybody see that intuition? So if this mean squared error, if the differences between the predicted O primes and the actual O's in the testing phase are less than 1 on average, then this thing has learned something. So far, so good? Okay, let's have a look. Okay. All right, let's have a look at this set of data over here for the simple robot. This is the worm robot. Green is the actual experiment. And you can see that on average, the error between O prime and O was 0.42. Again, 42 is a very auspicious number in our community. This was extra good news for us. Okay. Here's the permuted control and the random control. We just talked about the random control. Imagine a neural network in which we intentionally set all 4 weights to be random values. It actually guesses, the difference is actually about 0.47, not a distance of 1. Something's up. What's up?
The actual votes aren't randomly distributed.
The actual votes, the O's themselves, not the O primes, but the O's are not uniformly distributed between -1 and 1. They're very far from that, as we saw. So that's a statistical discussion, not relevant to our purposes for now. It doesn't actually matter what the value, the absolute error of random neural networks is. All that matters is that the predictions of the trained neural network is lower. The error of the predictions is lower than the random control. You can go read the paper. We did a second control, the test called the permuted control. We're not going to talk about that. Generally speaking, green is lower than blue and red, which is our signal that that neural network that we just talked about, this one, is able to learn a relationship between what the robot did and how the crowd responds without us having to make an assumption about jumping. Asterisk, kind of. We're still assuming jumping has something to do with touch information. Can't get rid of bias completely, but there you go. Okay. Same thing for the complex or quadrupedal robot. It's able, if it's the one that's training this neural network, this little part of its brain, it can, in theory, learn a relationship between what it did and how the crowd is likely to respond. Questions, comments? Okay, we were just talking about bias. Plenty of my bias here. If we want machines to understand language or understand anything about operating here in the real world with us, the best way, in my personal opinion, you form your own opinion, is that understanding has to be grounded in the social part. Imagine an autonomous vehicle that suddenly experiences a surprising event and it's got to try something new. It's far beyond its training experience. My hope for that autonomous vehicle is that in the few seconds that it's quote unquote deciding what to do in this new surprising environment, it is quote unquote thinking about how humans will feel about what it did in retrospect. In order to act safely in the real world, in my opinion, for machines, they need to be able to predict how people are going to feel about what they are about to do. Our dogs are not very good poker players. They don't have good poker faces. You can see it on their faces. They're doing something, and they have a pretty good prediction about how you're going to feel about what they're doing. Social intelligence. Okay, again, that's just my 2 cents on the issue. Cam.
Do you think we can achieve this like grounding of language in action sort of post hoc? We talked about last class, ChatGPT has gained this really deep understanding of these high-level symbols and how they interact with one another, but it's not grounded in this embodied interaction. But
Question mark. Maybe it is grounded. It's still an open question, right? Not in this way, but maybe indirectly ChatGPT is inheriting an understanding of humans and their world. Not quite clear yet, in my opinion. Sorry.
could we like more clearly ground it by taking that understanding, whatever it is, throwing it in a robot, and then trying to ground it
Maybe.
after gaining this understanding of the symbol?
Great idea. Do your ChatGPT thing, have it learn relationships between every word on the internet and every other word, and then expose it to sensor motor experiences and see if it can find a relationship between what it's learned up here among the symbols on the internet and what it feels in the real world. Maybe. Do we do this with our kids? Do it the opposite way around, right? Maybe we have no choice, just the way things go. Whatever humans are doing, it seems most likely they're doing maybe not this, but they're learning something about what they do and how mommy and daddy or the caregiver is going to respond. And kids very quickly get very good at making predictions about that. And then later, they start to read books and go to the library and read the internet. Should we do it? Which way should we do it? It's not clear. Does it matter? Maybe it doesn't matter. Okay, it's an interesting time to be thinking about these concepts. Obviously, we're in the AI high summer. Who knows? To be determined. Maybe some of you will figure this out. Okay, all right, that's enough about Twitch Plays Robotics, and that also concludes our discussion about all of the open challenges in the field. Obviously, there are many. We got 20 minutes left, so we are going to dive into the penultimate theme of the course, which is collective robotics. Like humans, for robots, there are many tasks that are difficult or impossible for a single machine to perform. So for many applications of robotics, it seems more desirable to deploy a large number of machines that can collaborate and cooperate to perform that task compared to one big complex machine? What might some of those applications be? Where does a swarm of robots make more sense than one big complicated machine?
When you've got a large area to cover.
If you've got a large area to cover, makes obvious sense. You'd like to have a large number of machines. Other situations.
Replication of a lot of things at the same time.
Replication of a lot of things at the same time. So if we want to parallelize effort, absolutely. Yep, good point.
When you want redundancy,
You want redundancy. What do you mean by wanting redundancy?
or robustness, when you want a system to be able to, take damage. If one robot dies, the rest of the robots can achieve the task.
Absolutely. So doing something over a very large spatial scale, doing things in parallel, doing things robustly. If any one member of the swarm fails for whatever reason, the rest of the swarm can carry on. Just from those three observations, hopefully you can start to appreciate that there are many, many, many tasks for which large numbers of robots are more useful than one. There's no free lunch. There's always a cost. What is the cost of designing, training, and deploying large numbers of simpler machines compared to designing, training, and deploying one big, complex, complicated machine? What's the cost?
Effectiveness.
What do you mean by effectiveness?
So like, if you have a lot of robots, but they're too simple, you might not get as good of a result as the one that's like more complex.
Great point, right? We might make them too simple. They're not effective. Yep. What other costs are at play here?
Material cost, if you're doing a bunch of them, and expensive.
Absolutely. So NASA loves the concept of collective robotics. Obviously, they have literally a lot of real estate in this solar system to explore. They would love to send 1 million rovers to Mars. They can't, because you can't put them all in a rocket, right? Material cost, volumetric cost, how much literal 3D volume does a robot take up, weight, and so on.
If you're building one robot, you are more likely to notice big flaws. But if you're building lots of robots and your attention is maybe divided, you might not notice the one flaw that takes out all of the machines.
Great point. The one flaw that takes out all the machines. The other thing that's scary about deploying very large numbers of things is that they all have a common Achilles heel, right? I thought we learned this lesson early on with computers, that a virus that can attack and bring down one operating system, by definition, can bring down every other instance of that operating system. Unfortunately, we still seem to be developing technologies in which there's only one or a couple of operating systems in play. Not a good way to do things, right? We've created a technological monoculture. We have a large number of these things that all inside look and act almost identically. Not a very good idea. There's a cost to making large numbers of things. One of them is making them too similarly makes the swarm as a whole vulnerable. Another good hidden cost. Other costs of swarms.
I'm imagining, like, in an evolutionary sense, like, I forget the exact term, but when like a fish has like 1,000 babies, like not a lot of them will survive, but like a few will make it because they're all a little bit different.
Absolutely, right? So maybe back to material costs. We might deploy a large number, but most of them fail. It's a very wasteful, effortful thing to do.
You also have to take the time to develop a way for them to communicate, especially if they're going to be working close together.
Why do they need to communicate?
So that they don't trip over each other or break each other by proximity.
Okay, maybe. So I'm sort of giving away the punchline here. Once you get to a certain level of sophistication in a collective entity, either a group of humans or insects or machines, it usually makes sense for them to communicate. Although I will give my usual warning here, thinking about thinking is misleading. What collective tasks actually require explicit communication? Which can get away with implicit communication? And which require no communication at all? I just wanted to pose that question to you. We will come back and tackle that question next week when we get to lecture 21, the issue of communication. Obviously, communication can be helpful in very large collectives. We are part of an 8 billion collective, and we tend to communicate explicitly amongst ourselves. Not all large collectives explicitly communicate, or at least not that we're aware of. Okay, we're going to talk first in lecture 20 about coordination, doing something collectively together more easily than one doing it alone. And then we'll talk about communication next week. Okay? All right, so let's start with coordination and swarms. Obviously, lots of examples of this in nature. Here are starlings doing what starlings do best. Which starling is in charge? Wouldn't it be great if humans could do this? Large coordination, no one's in charge. We haven't quite figured this out yet, but clearly it's possible. Okay. Flocking in birds, schooling in fish, herding in land-based organisms. It's ubiquitous in nature. Mother Nature has rediscovered collective behavior over and over and over again. The cells inside your own body coordinate. They are themselves a collective. For the obvious reason that coordination is a good way to do things. Often it makes sense for large numbers of simple things to do things collectively than to try and do them on their own. Much fodder here for biological inspiration for us, trying to create large numbers of machines that coordinate their efforts. We're still not that good at it yet. Okay, but we're working on it. Here's one of the places where we started to work on this. This is work by Craig Reynolds, who back in the 1980s, he was a computer graphics researcher, wanted to create computer graphics of very simple animals coordinating their actions. So he simulated some very simple animals, these little triangles. These later became known as boids, B-O-I-D. If you Google Boyd or Boids, you'll find all of this work there. In an individual Boyd, it is simulated inside a simulator. This is 1980s. No physics engines existed, so Craig had to write all of this himself. For each individual Boyd in the Boyd swarm, it had a circle of sensation. It could see a certain distance around itself. And at every point in time, each Boyd looked inside its circle of sensation and noted the relative position of any of its peers that were inside the sphere. So in this example here, the green Boyd knows that it has 3 of its peers on its left. In this particular example here, this different Boyd at a different point in time knows that there are 6 peers surrounding it. Each Boyd knows the relative position of all of its neighbors inside the sphere sensation, and it also knows the heading of all of its peers. That's the little line emanating from the front of the triangle. At every point in time, the Boyd was trying to update its new position and its new orientation. How did each Boyd decide what its new position and new orientation was? First, each Boyd would run 3 separate functions. The first function is the separation function. It would compute the relative positions of its peers and steer or alter its orientation so it would point away from its peers. So it's updating, comes up with a little delta for its orientation. It's going to try and turn away from its peers. Before it moves, it also runs the alignment function, which computes the average heading of all of its peers. And the blue line here represents the mean or average of all of its peers' headings. And this function returns another delta in orientation, another suggestion for how to change orientation so that the robot's orientation at the next time step will more closely approximate the average heading of its peers. So an individual peer has run separation, gives back one suggested change in heading. It runs alignment, gets back a second suggestion in a change of heading. And finally, it runs cohesion, which again gives back another delta, which is steer towards the average position of all of the peers. So we've got 3 deltas in orientation. After the Boyd has run all 3 of these functions, combines them, sums them, and takes the average, and then updates its heading accordingly. Every Boyd runs exactly these 3 functions at every time step in the simulation. So far, so good? This is the result. Again, you'll have to excuse the 1980s graphics here. This was state of the art at the time. Who's in charge? No one's in charge. Why do the Boyds flow around the cylinders in their environment?
Is it because it cuts off the view of the other voids that are past the pillar, so they're only being drawn towards the ones away from the pillar?
Kind of. So it's obviously if you have a pillar on your left, you cannot have any piers over here. If you've got these piers over here, the cohesion algorithm is going to pull you towards your piers. The Boyds view anything in their environment as a peer. They're very social. Everything is part of the flock. So they're also being crowded by a whole bunch of individuals over here. It's not a whole bunch of individuals, it's the cylinder, which is causing it to try and separate or move away from that cylinder as well. Right? The Boyds are not very bright. This is all they do. They don't distinguish between cylinders, piers, this pier, that pier. With these very, very simple rules placed into a large number of these Boyds, you get relatively sophisticated collective behavior. This was shocking at the time. And for some people, it's still shocking to see you can get these relatively elegant collective behaviors from relatively simple rules. When you watch the starlings or a very large school of fish, you immediately realize no one is in charge, but it's easy to start to think that whatever they're doing is pretty sophisticated. Maybe not. Remember the lessons of Valentino Breitenberg and the Breitenberg vehicles? Often we overthink things. Maybe what starlings are doing and mackerel and wildebeest and so on are maybe not as complicated as we think. They may not be running this in their heads, but this seems to be enough to get things that look very much like herding, flocking, and schooling. Okay, so this was the 1980s, and there we go. As I mentioned, Craig Reynolds was a computer graphics researcher. He started to share his results with other computer graphics professionals, some of whom worked for Disney. And in the 90s, we started to see movies like this. Any movie you watch today that has any large simulated crowd scene, it is running that computer algorithm that generated that clip for that movie. Somewhere down in the depths of that computer algorithm is the Boyd's algorithm. This was the beginning. You can layer on, as you can imagine, it's quite a modular algorithm. You can start to add on other nuances to how each individual in the swarm alters its behavior. Did we miss it already? When the wildebeests are coming down the Box Canyon, they flow around this spur of rock. You know why that particular scene is in this movie. Now, Okay, huge impact on the computer graphics community and film community, as you can imagine. Also an impact on the robotics community. This was, again, a wake-up call that if we want to create collective behavior, maybe we can write down these simple functions. It turns out in practice that doing this is tricky, not that easy. So what a surprise. In the 1990s, some evolutionary roboticists came along and said, let's evolve these functions against a fitness function that doesn't reward for the behavior of an individual, but rewards for the behavior of a group. So what we're going to see starting today and then into next week is an evolutionary robotics experiment where they're going to evolve behaviors for individuals in a collective and reward or provide a fitness value back to the group as a whole. Perhaps not great from a public relations point of view, but these roboticists chose collective hunting. So here we go. All right. One of the reasons why it's useful to work in a group, if you're a hunter, is your prey is pretty canny. You'll remember I included this slide to remind us of Alexander's book on the principles of animal locomotion, and also our discussion about how the fact that brains tended to evolve to orchestrate motion. Everything that the brain does ultimately can be traced back to evolutionary pressures for us to coordinate how we move about in the real world. Tell me about lions and Thompson's gazelles. Why do lions hunt as a pride rather than as an individual?
Because their top speed is much, much lower than the gazelle's top speed.
Absolutely. So imagine this particular lion and this particular gazelle, and let's assume that this lion is deprived of its pride. There's none of its peers around. It's got to bring down the gazelle on its own. What are the chances? If you were this lion and you were extremely hungry, you don't have time to wait to go find your pride, what do?
You've got like a 4-second window to catch it.
You've got a 4-second window to catch it. So what do? You either know consciously or subconsciously about how much time you have. What do? You're the lion. You sneak up on it. We were just talking about dogs. Anyone have cats at home? They're very good at getting low and sneaking up on things for this reason. So this is just meant to illustrate, again, there are certain things that are just difficult to do on your own. Literally. If you can bring down the gazelle in less than 4 seconds, knock yourself out. If you can't, or that's a rare thing to do, you have an alternative strategy available to you, which is try and recruit your peers to work collectively. But how? How do you work collectively? Okay, so we just spent some time on the actual Serengeti Plain in Africa. In this paper from 1996, we're going to travel to a virtual Serengeti that looks like this. We've got 2 minutes left, so I'll just introduce the playing field here. We've got this plain, and we're going to evolve behaviors, or these researchers are going to evolve behaviors for these 4 lions. And the fitness, a single number that we're going to apply to all 4 lions, is how well they bring down this virtual gazelle in the virtual Serengeti plain. Again, this paper was published in '96, 4 years before physics engines, so these researchers created their own very simplified physical environment. Simulated physical environment. They placed the 4 lions at random positions on this 15 by 15 unit long virtual plane. They placed the gazelle at a random position on this plane. What happens if the gazelle or the lion gets to the edge of this plane? I don't know, falls off the edge of the world. So these researchers took this virtual Serengeti plain and they folded this 2-dimensional sheet so that the long top half came into contact with the long bottom half. So we now have a tube. And then they took that tube and bent it so that the 2 ends of the tube touch. And we now have a donut or a toroid. So I want you to imagine 4 of these virtual lions running on the surface of this toroid. Same for the gazelle. Like us, they now live in a world that has no edges. They can run forever. Everybody see that? Okay. Good mental image to leave you with today. You have a quiz due tonight. You're working on your final project. Have a good rest of your week. See you Tuesday.